Well, thank you, Hella, for that introduction, and thank you to the Royal Institute and to the RASC for both asking me to speak and for the excellent lunch that I had. And lastly, thank you to all of you for coming along today to hear me talk about what I love. I'm going to tell you about the future of astronomy, but before I do that, I need to tell you a little bit about the past. Now, astronomy, one would argue, is the oldest science there is. Our ancestors have been looking up at the sky and trying to understand for thousands, if not tens of thousands of years. So it's important to understand and remember that the history of astronomy does not begin with Galileo, but that humans have had a very close relationship with the stars ever since we were humans. Now, I only moved to Canada a year ago, as you can tell from my accent, so I'm still learning about the stories that the Indigenous peoples of Canada have and had with the night sky. But let me bring to you one of many wonderful stories from down under. Here is a picture of the Milky Way, as you would see it on a dark night in Australia. Anyone who's been to the Southern Hemisphere knows that our Milky Way is better than yours. Not just because the Southern Hemisphere is emptier of people and light, but just because the galaxy is brighter in that direction. But this is the spectacular Milky Way you see from a dark night in Australia. It's so spectacular that if you walk outside on a dark night, I recall vividly ducking my head, thinking I was about to hit my head on something that was actually the Milky Way. So a modern understanding is that this is stars and gas and dust, the backbone of our great galaxy, but of course, to many Aboriginal groups, they saw it as something different. They saw it as an emu in the sky. And if you look very carefully, there it is, the emu in the sky. And once you see that it's an emu, all of the Western, Roman, and Egyptian constellations are gone forever, and you only ever see the emu. If we move on to the modern technological age of astronomy. So Galileo, of course, did not invent the telescope, but he was the first person to use a telescope to look at stars. And for the last 400 years since then, our traditional telescopes that use optical light, the same light that our eyes use, have become more and more sophisticated. So many of my colleagues would be horrified that I'm only going to spend one slide on 400 years of astronomy, but this is my talk and I get to do what I want. But let me summarize to you the achievements of traditional optical astronomy, the way in which we've been able to take the light from the night sky and to learn more. One of the greatest leaps forward about 100 years ago is that we realized that our Milky Way was not the only thing in the universe, that there were many Milky Ways, there were many other galaxies like this, each one of which was hundreds of billions of stars, and that our Milky Way was simply one of these galaxies. Once we realized that all of these fuzzy patches on the sky were galaxies in their own right, people started to measure their distances and their motions, and Edwin Hubble discovered that all galaxies seemed to be rushing away from us, that the universe was actually expanding. More recently, in the latter halves of the 20th century, people began to measure the locations in 3D of thousands and then millions of these galaxies, and found that they weren't just scattered randomly like throwing salt on a tabletop, but that they're organized into an incredibly beautiful and complicated cosmic web. That there are some parts of the universe that are full of galaxies. Every little dot that you can see here, in fact you can't even see the dots because they're blurred together, represents galaxies. Chains of galaxies like the walls of a soap bubble, and then inside the bubble there are these enormous cosmic voids, some of the largest objects in the universe, where there are no galaxies at all. And then perhaps the most stunning and unexpected thing is that when people began to measure using optical telescopes the rate at which galaxies are moving away from us, they discover that galaxies are moving away from us faster and faster. So we don't just live in an expanding universe, but we live in an accelerating universe, named as the breakthrough of the year in 1998, and won the two teams that found it the Nobel Prize in Physics in 2011. And the interpretation we have at the moment is that the universe is accelerating because it's filled with something called dark energy, some sort of mysterious anti-gravity force that's actually pushing the universe apart. Of course, dark energy is just a name. It doesn't tell us what it is, and good thing it doesn't, because we have no idea what dark energy is. It's one of the great unsolved problems in astronomy is what is 70% of the universe, what is dark energy? So all of these great discoveries and many more have all come from traditional optical astronomy, simply looking at the same light that our eyes see with a much more powerful device than our eyes and studying the positions and appearances and locations and motions of stars and galaxies. But there is a whole other world out there. Our eyes can only see one tiny sliver of what we call the electromagnetic spectrum. Light is a wave. You can think of it as sort of a ripple moving towards you. And if you take that wave and you squash it and make the wavelength shorter, you then move into a whole invisible universe over here. So if you make light the wavelength shorter, you move into the ultraviolet, the type of light that gives you a suntan. Make it even shorter and you turn the light into X-rays, which of course we use to look at broken bones, and make it even shorter again and it turns into gamma rays, which are very harmful radiation. So you've all heard of ultraviolet and X-rays and gamma rays. They aren't some mysterious form of radiation generated with special equipment. They're just another form of light that your eyes can't see. Similarly, if you take light and you stretch it out to longer wavelengths like you're seeing here, you then move into the infrared part of the spectrum. You think of infrared as night vision goggles or heat vision, it's just another form of light. Stretch it out more and you get microwaves. The microwave radiation that we use to heat up our food in a microwave oven, it's just a special form of light. And stretch it out even more and you get to the least energetic form of light, radio waves. The radio signals that we use to talk on our mobile phones, that we use to pick up broadcast television and to listen to AM or FM radio is just another form of light. If you could see radio waves with your eyes, which of course you can't, but if you could see them, when you were talking on your phone, you would see the actual phone blinking and shining a light and the cell phone tower blinking and shining a light as if they were communicating with flashlights or mirrors. So all of these forms of radiation that we are very familiar with and we use every day are just different types of light. Now, the fact that we can only see one small part of this glorious spectrum, well, that's our problem, not the universe's. The universe happily radiates in all of these different types of radiation. So when we look up at the night sky and see stars and galaxies, we're just seeing one tiny part of the story. There are other types of objects in the night sky that radiate in X-rays or in ultraviolet or in infrared or in radio waves. And for the rest of this talk, I'm going to tell you about what you see when you look at the radio universe. And if you're thinking, well, what does it mean to look at a radio wave? Let me give you a different way of thinking about it. If you take an old school FM radio that still has a dial, and you find somewhere on the FM dial where there is no radio station, you hear static. And a big part of the static that you're picking up on your FM radio is actually the hiss and pop and crackling of the radio waves coming from the sky. So if you don't like the idea of looking at radio waves or putting on radio goggles, think of radio astronomy as listening to the sky. In optical astronomy, we look at the sky, and in radio waves, we listen to the sky. We listen to that hissing and that crackling, and we turn it into pictures. Now, in practice, if you actually go to an observatory, we don't tend to actually put the headphones on too often, but we could if we wanted to, and we could listen to the sky. Even to a trained ear, it does sound like static, but complicated, powerful computers can convert that into spectacular, beautiful images of what the radio signals from the sky are telling us. So radio astronomy only began really in the 1950s. The first radio astronomy was actually done in the 1930s, but it was largely ignored, but became to prominence after World War II. Here in Canada and Australia, the US and Netherlands, you had all of these radar technicians who suddenly didn't have to track enemy airplanes, and they used their radars to start looking at the sky. So a radio telescope looks very different from an optical telescope. Here is sort of a classic radio telescope. These are representative of the sorts of giant dishes that were built throughout the 1950s and 1960s. This particular one is 64 metres or 200 feet across. This one is located in Australia in a place called Parkes, but there's a copy of this one that was built later in Algonquin. If any of you have been up to Algonquin National Park, there is a dish that looks exactly like this one and is still used today for scientific research. So this is essentially a giant satellite dish, and by steering it to the right place, you can listen to the static of the sky and reconstruct beautiful images of invisible radio waves. So radio astronomy has only been around for about 60 or 70 years compared to the centuries of optical astronomy, but it's made some great discoveries. So some of the early discoveries of radio astronomy was that some of the most powerful objects in the universe are giant black holes sucking in huge amounts of gas, but also squirting out other parts of gas in long, thin jets at almost the speed of light. So what you see here is the white stuff is a traditional optical image, but superimposed in purple is the radio image that you can reconstruct from telescopes like this one. And what you see is this energetic black hole here that is shooting out jets over millions of light years in opposite directions at almost the speed of light. And that was this energetic, violent universe that was revealed to us through radio astronomy. Before radio astronomy, there was a perception that the sky was calm and quiet and soothing and unchanging. What radio astronomy revealed to us is the universe is actually a violent, destructive, constantly churning and changing place. Another amazing discovery from radio astronomy, which also has won so far 2 Nobel Prizes and probably will more in the future, is that there are some very strange things out there in the sky. That when some stars die, they collapse into these tiny balls not much bigger than the GTA called neutron stars. And that these neutron stars rotate very precisely, and they shoot beams out 2 ends like a lighthouse, and you get this regular heartbeat or pulsation from them. So we never see a picture like this. We only ever see sort of a chart recording like this, but it turns out that these are some of the most stable clocks in the universe. They're more stable than our best atomic clocks, and we can therefore use them to actually understand the nature of space and time and gravity. And again, those were discovered through radio telescopes. And then perhaps the most amazing radio discovery at all is that in radio waves there's a faint hiss or static coming from the whole sky. If you look past all the individual stars and galaxies, the whole sky is glowing in the light of radio waves. And this is actually the remnant glow from the Big Bang itself. We believe that the whole universe began in a Big Bang 13.8 billion years ago, and that event was incredibly hot and dense. And over the last 13.8 billion years, the heat from that has gradually cooled to a temperature of about minus 270 degrees Celsius, but that's still warm enough to produce a very faint glow over the whole sky called the cosmic microwave background that we only see in radio waves. And that too has won several Nobel Prizes. So not that we're keeping track, but so far optical astronomy has only ever won 1 Nobel Prize, and radio astronomy has won about 5 or 6. So the things I just described to you were great discoveries of radio astronomy pretty early on. The 3 discoveries I just showed to you, quasars and pulsars and the cosmic microwave background, those are really all discoveries made in the 1960s. But it would be completely misleading to think that radio astronomy's heyday was the 1960s. It continues to be at the forefront of discovery. The first thing is that technology's come a very long way, and that radio telescopes now look very different. So here are 2 types of modern radio telescopes, and I'll be talking about these 2 types a fair bit in my talk. The first type is called an array, where you take these traditional dishes and you link them all up electronically. So the bigger the dish, the more you can see. You can see fainter things and you can see finer details if you build a bigger dish. So you might start off with a 10-metre dish, and then a 20-metre dish, and a 60-metre dish. The biggest steerable dish that's ever been built is 100 metres across. And even that's not really big enough to see much. So you say, well, why don't we build a dish that's 500 metres across or a kilometre across? And you quickly start running into practical engineering problems like, how do I steer this thing? So we'd love to have a single radio dish a kilometre across. We'd love to have one that's 1,000 kilometres across. But it's impossible to build a steel dish 1,000 kilometres across. The way you get around this is you build lots of small dishes, you link them electronically, and then you use a computer to simulate one giant dish. So I can put one dish in Vancouver and one dish in Montreal, link them up electronically, and I now have a dish the size of Canada with all of the amazing power of vision that that would entail. And so that's quite routine now, and just to add to what I said earlier, the realization that you could make these arrays and link them up, that won a Nobel Prize too. So we have these arrays. But these dishes are still traditional dishes. They're made of solid steel in a curved shape, and they steer and they point. And it's quite magnificent when you see these arrays of dishes. Here's an array of 5, but there's one in New Mexico that's actually 27, and you see them all steering in sync across the sky. But there's a new type of radio telescope. They're essentially a glorified version of the rabbit ears or coat hanger that you might see on an old car to pick up the radio. And these are these metal spiders that have no moving parts at all. And rather than steer, these spiders can see the whole sky at once, and again you use a computer to essentially steer it in software and make pictures of the sky. So these telescopes are cheap to manufacture because there's no moving parts and they're just small parts, but the supercomputers become very expensive. And so these new types of telescopes, the sorts of telescopes that are being discovered right now, and these that are being made right now, and these are the telescopes that are making new discoveries. So I could spend a whole hour or more walking you through all the great discoveries that have been made by radio telescopes in the last few years, but let me show you 2. They're both discoveries by me, and unfortunately they haven't led to any Nobel Prizes yet. The first one is that we've realized that when you look at empty space, you normally just see nothing, but that what we call space, well, space is a terrible name for it. It should actually be called stuff, because space is actually filled with invisible gas in the same way that there is gas in this room right now. So you know that there is gas in this room right now, you are breathing it, and if you move your hand around, you can actually feel the breeze from that gas. But what you cannot see right now is that that gas is actually swirling around, it's flowing in through the vents and under the doors, and every time you breathe, you see it when it's cold, but right now you can't see that there's sort of turbulence and swirls in your breath. If we sort of sprinkled smoke into the room or something, you'd be able to see all the airflows. What we'd really like to do is to do that in interstellar space, to see that gas and to see the swirls and turbulence, what one of my colleagues referred to as the interstellar mosh pit, that actually makes all the gas in the galaxy flow around and eventually collapse and form stars. So we realized that using radio telescopes you can actually do that, and a piece of the sky that formerly was invisible, we now reveal that mosh pit. This area here is what's called the galactic plane, so we like to call this the snakes in the plane. This is the invisible swirling and squirming and swirling and vortexes and spirals and collisions of all the complicated invisible gas of interstellar space. Another discovery that I was involved in quite by accident was I was sitting in my pajamas on the couch a few days after Christmas in 2004 when I got an email from a friend marked urgent, and what she had told me was that she believed, based on her calculations, that a star had just given off a flare, and this flare was 2,000 times brighter than every star in the Milky Way put together, and that we should have a look at it. So we steered our radio telescopes towards this star, and what we saw was the brightest explosion in the history of humanity. Pure luck that we happened to hear about it and then see it. We saw this star that's 50,000 light years away, and it was so bright that its radio waves actually changed the structure of the Earth's magnetic field from 50,000 light years away. So we had not realized that individual stars could put out bursts of energy so bright that they can affect the Earth from 50,000 light years away until we looked at them with our radio telescopes. The best analogy I can give is that if you were a chemist or a biologist looking at some slide under the microscope, suppose you look at it and you say, that's interesting, and you're just about to throw it in the bin when a hand comes out of that slide and punches you in the face. We're not used to our experiments affecting us, but this star actually changed the structure of the Earth's magnetic field. So this allowed me to tick off one of the things on my bucket list. I got to be in the New York Times. I described it as whoppingly bright and got lots of angry people writing to me saying that if they wanted to see words like whoppingly, they would have read the New York Post. But suffice to say that radio astronomy is still making many great and unexpected discoveries of how wonderful and how powerful the universe is. So if you put all the things I've described together, starting with ancient astronomy of our ancestors, through the area of optical astronomy and radio astronomy into the 21st century, you get to this incredible point where I can show you the entire evolution of the universe on one slide. If I had given this lecture to the Royal Institute 100 years ago and said, I'm going to put the entire history of the universe on one slide, I would be mocked. But I can do it now, and everything I'm showing you has been in textbooks for decades. So the fact that there's nothing even controversial about what I'm about to show you is truly stunning. But here is essentially the astronomer's answer to the question, where do we come from? So we know that when stars, big stars, reach the end of their lives, they explode in catastrophic explosions called supernovae. The star blows up. That throws the outer layers of the star out into space at very high speed and produces a beautiful, essentially expanding bubble or smoke ring of debris moving outwards into space. That's where all that gas, I told you that the universe isn't empty, that's full of gas. Well, that's where a lot of it comes from these explosions that throw debris into the galaxy. So that gas hangs around for a long time, but eventually it starts to coalesce, and under the forces of gravity, it starts to collapse and form dense clouds like this one. And eventually those clouds become so hot and dense and small that the fires of nuclear fusion ignite within them, and that creates new stars. And those stars will shine for millions or even billions of years, but eventually they will age and they will die, and the whole process begins again. So not only have I shown you the process that drives the whole universe in one slide, I've only used 7 words or so and 4 pictures. And as I said, none of this is controversial. All of this is accepted astronomy, quite profound realization that I've shown you on one very simple slide. So what we know is that just like Toronto, the universe is very good at recycling, and that new stars are made out of old stars, and those old stars are made of the stars before them, and those stars are made of the stars before them. So you might have heard the line from Carl Sagan and others that we are all made of stardust. That's not just someone being poetic, it's physical established fact. Every atom in you, every atom in every person who's ever lived, every atom on this planet was once part of an exploding star, a cloud of gas, a new star forming a nebula. By the same token, we too will eventually be returned to the cosmos, and the atoms that are in us now will one day be part of new stars billions of years from now. So that's quite a stunning realization that we are made of stardust and that we are just one step along the way of a cycle that has billions of more years to run. So on the one hand, astronomers can strut around and feel very proud that they have uncovered the question that was only supposed to be for philosophers. We have answered the question of where we come from. On the other hand, there's a big, big problem with this cute argument, and that's that it doesn't make sense. Because the universe has only been around for 13.8 billion years. So our star and us were made from some previous star, and that star was made from some star before that, and that one made from before that, but that doesn't solve the problem, because it's a chicken and egg problem. Well, if that's how stars form, if stars can only form because other stars give their lives to make new stars, well then, where did the first stars come from? So we might be able to answer where stars come from now, but the very first stars, the stars that formed shortly after that Big Bang 13.8 billion years ago, they must have formed in a different way, because they could not have formed from the debris of the stars that preceded them, because there weren't any stars that preceded them. So how do we answer this rather embarrassing question that we don't know where the first stars came from? So the answer is hidden in an era of astronomy known as the Dark Ages. And we call it the Dark Ages because there were no stars. It was dark. So the first thing to realize, and many of you probably know this, is that light travels at a finite speed. It's a very fast speed, 300,000 kilometres every second, or 7.5 times around the world every second, but it is a finite speed. And so if I look at something a long, long way away, I do not see how that object looks right now, but I see how it looked some time ago, and the light is only just getting to us now. So when you hear expressions like 10 light years away, a light year is not a unit of time, it's a unit of distance. It's the distance that light travels in 10 years. So what that means is that if I look at a star that's 10 light years away, I am not seeing what that star is doing in 2016, I'm seeing what that star was doing in 2006. If that star were to, say, give off a bright flare right now, the star would look completely normal to us, and we would have to wait till 2026 until we saw that flare. Incidentally, that means that that incredibly bright explosion that we saw in 2004, it was 50,000 light years away, meaning it actually happened in 48,000 BC, and for the whole of human history, that flare has been coming towards us, that we only saw it in 2004. So this is sort of annoying and it's hard to see what's happening right now, but it's also exciting because it means that we can actually use the universe as a time machine. And if the further away we look, the further back in time we go. So you might say, well, why don't we actually see the Big Bang then? This is great. All we have to do is find something 13.8 billion light years away, and that is something at the Big Bang. We should be able to point our telescopes between all the stars and the galaxies, and we should be able to see the Big Bang right now. Well, it turns out that doesn't quite work, because the most distant thing you can see, the thing you see if you look between all the stars and the galaxy in front of it, is you run into that faint glow that I described, the cosmic microwave background. And that's not the glow of the Big Bang itself, it's a glow that was produced about 300,000 years after the Big Bang. So this is a zoom in on that cosmic microwave background, that glow coming from the whole sky, and you can see all these little lumps and ripples. The universe wasn't entirely smooth, it was lumpy, there were hot bits of gas and cold bits of gas, and that is the most distant thing that we can see. The record for the most distant thing in the universe that we can see is this glow from the cosmic microwave background, almost 13.8 billion light years away, this glow from just 300,000 years after the Big Bang. So okay, that's what the universe looked like 300,000 years after the Big Bang. There are no stars yet. Why don't we just look in front of this and watch the first stars forming? So if you look in front of this, you sort of refocus your eyes, so to speak, and say, well, what's the next thing you see in front of this? You get a bit of a surprise, because the next thing you see about 1 billion light years closer is stars and galaxies. Now, they are different from the stars and galaxies that we see today, but they're stars and galaxies. So somehow in just 1 billion years, which is a blink of an eye for an astrophysicist, the universe has gone from just being this warm, lumpy soup to a very complicated, structured thing with stars, galaxies, probably planets. And so one of the big problems in modern astronomy is you want to know what happened between here and here. This phase is called the Dark Ages. This dark because we don't know what happened, and dark because there were no stars yet, when the first stars turned on and this process of recycling began. So what happened in between these two? There is one way we can find out. We can't use normal telescopes to look for the stars because there are no stars. But there is all this gas, this goop and blobs floating around, and it turns out that if you just get a big pot of gas, it glows very faintly in radio waves. Essentially, if you have a big enough pot of gas, it gives off static. And so if we could detect the glow in radio waves from the gas millions of years after the Big Bang, we could use that to watch the first stars form and understand ultimately where we come from. You can work out how bright the glow from this gas should be, and it turns out that even our most powerful telescopes are not powerful enough to detect this faint static, this faint hiss, this radio glow from the clouds that are forming into the first stars. So people realized in the early to mid-90s that if we wanted to finally solve this question of where did the first stars come from, that we need a bigger telescope than anything we have today. And so this started off as just a conversation that astronomers like to have around a beer. I wish we had a bigger telescope. Pretty much that's all any other astronomer complains about. But this then quickly coalesced into an international effort around a project called the Square Kilometre Array, or SKA. So an array, meaning lots and lots of dishes connected together, and a square kilometre, not because the dish is a kilometre or because anything is square-shaped, but because if you added up the area of all the dishes combined, the total area would be 1 square kilometre. So that's a lot of steel, but that's how much you need with lots of dishes, thousands and thousands of dishes combined, all electronically linked, to have enough sensitivity and enough power to detect the glow from the first stars being born. So this has been a wonderful grassroots effort. It started off as just an idea, and then gradually there were committees and plans, and then organisations and meetings, and eventually governments becoming involved. And now we have this fabulous international commitment to build the most powerful telescope ever constructed. And so there are currently 10 countries involved in doing this: Australia, China, India, Italy, the UK, the Netherlands, New Zealand, South Africa, Sweden. And one of the founding members, one of the first 6 countries to put their hands up and saying, let's do this, was Canada. And just launched on Friday our brand new Canadian SKA telescope website, skatelescope.ca, also en français. Please check it out, and you will learn a lot more about what Canadians are doing to make this telescope happen. So the very first question I always get is, well, how much is this going to cost? And the answer is a lot. About $1 billion. It was less than that until the exchange rates went the wrong way. About 600 million euros, so about $1 billion Canadian dollars. That sounds like a lot, but it's spread between 10 countries for a telescope that's going to last about 50 years. When will this telescope be ready? Well, we hope to begin construction in about 2 more years and to begin making scientific observations with it in 2020, which is not that far away. And well, what will it look like? Well, we actually have to combine 2 different technologies to be able to measure all the signals we want to measure. I described to you the 2 different types of telescopes we have now, the steerable dishes and sort of the fancy coat hangers or metal spiders. And here is an artist's impression. Firstly, the dishes, about 3,000 dishes, all linked up electronically, spread over thousands of kilometres. And then here is sort of these fancy coat hangers, again, in this case about 250,000 of them, again spread over hundreds, if not thousands of kilometres, and linked up electronically. And so the square kilometre array has 2 different types of technologies that work in concert, and both of them are far, far beyond anything that we've ever tried to do before. So of course, the $1 billion question is, where do you put this telescope? So the first thing is, it's got to be on a place with lots and lots of open space. You can't build this thing on top of a mountain like an optical telescope. You need thousands of these dishes, all linked together by optical fibres, so you need a lot of open space. So you also have to put it somewhere where there's actually infrastructure. You need airports, roads, power, internet, electronics, because this is a complicated, sophisticated instrument, and it needs to be built, it needs to be repaired, people have to live nearby it to fix it when it goes wrong. So you need a place that's in the middle of nowhere, but which has lots of infrastructure. You don't want to put it at the North Pole or the South Pole, because then you can only see half the sky. You want it somewhere not too far from the equator, so that you can see big chunks of both the northern and southern skies. And the most crucial thing, the most important thing for a radio telescope is in the same way that with an optical telescope you want to put it far from the city lights. It's not city lights that are a problem for radio telescopes, it's radio interference. So our whole modern civilizations are based on communications and radio technologies. We have mobile phones, we have radio, we have TV, we have microwave ovens, we have cars that create pulses of radio energy every time you use a spark plug. If you put a radio telescope in Toronto, it'd be totally useless. It'd be like trying to listen to a whisper from the moon when everyone is screaming in your ear. And so, in the same way that an optical telescope has to be put somewhere where it's dark, a radio telescope has to be put somewhere where it is quiet from a radio perspective. So you have to somehow find a place on Earth where there is an FM radio, where there is an AM radio, where there's no TV, there's no cell phone coverage, where there's nothing. So meeting all of these requirements is not easy. This was a process that went on for about 10 years, but just to show you one of the considerations, this is a map of the world showing you how noisy different places in the world are based on how much radio communications there is, how much people on their phones, FM radios, and so on. So you can see that Toronto is not a good place to put a radio telescope because, not surprisingly, there's all sorts of things happening here: planes, satellites, mobile phones, radio stations, and so on. Europe is also a no-go zone. This image is about 10 years old now. Asia was already pretty bad, but it's probably much, much worse now. And so there's not that many places that you can put a radio telescope and know that it will be useful. And what's more, you might say, oh, well, South America's looking pretty good, but we know that 20 years from now, South America will probably be very bad, and that there are places that don't have a lot of mobile phone usage in remote parts of South America now, but that's going to change rapidly. So after 10 years of very careful site studies and all sorts of remote locations around the world, there was a realization there's really only two possible places that you could put this telescope to meet all these conditions. One is in the middle of nowhere in southern Africa, and one is in the middle of nowhere in the western part of Australia. And so both of these have lots of open space, there's quite a bit of infrastructure, they're not too far from the equator, and most importantly, they are radio quiet. And so there was this sort of Olympic-style bidding, South Africa versus Australia, and in the end the decision was made that the two different types of technologies, the steerable dishes and the metallic spiders, actually needed slightly different requirements. And the decision was made, just like the wisdom of King Solomon, to put the dishes here and to put the spiders here. So we have one observatory with two different sites. That's not that common, that's not that unusual in astronomy. The dishes in South Africa and the spiders in Australia, each one linked up on its own, but also with a capability to operate together. So where exactly are these? Well, here is the South African site of the core of the Square Kilometre Array. So here's Cape Town and Johannesburg off here somewhere, and about an 8-hour drive to Cape Town in this desert area. In fact, in South Africa, pretty much everyone lives in this area. Nobody lives in this, almost nobody lives in this section here. It's all just desert. And so there's a site here where the Square Kilometre Array is now beginning to take shape. So it was pretty empty, but enormous amounts of construction and capital works funded by the South African government to put in roads and power and electricity and everything else. Similarly in Australia, so here is Perth, which is the most isolated city on Earth. The quickest way to get to Perth from here, by the way, is simply to go straight down. If you look at the opposite longitude and latitude Toronto, it's pretty much exactly Perth, so it's a long way from here. And again, about 8 hours drive from Perth, in the middle of nowhere, is what's now known as the Murchison Radio Astronomy Observatory. It's been established as an official observatory. There is legislation now to demand that this be kept radio quiet, in the same way that if you find some beautiful virgin rainforest, you can pass legislation to keep the forest preserved. We have done the same thing here for this radio observatory, and enormous amount of respect and interaction with the Wajari Yamaji people, who are the traditional Aboriginal owners of this land. And the Australian site doesn't look that different from the South African site, sort of in the middle of nowhere. As I said, it's quite important that when you go on site, you turn off your phone, you have your laptop shielded. Just because we're the ones that are benefiting from this radio quietness doesn't mean that we can make noise any more than a park ranger is allowed to chop down trees in a protected forest. So working on this site is quite challenging, firstly because it's 45 degrees Celsius every day, secondly because if your screwdriver breaks, it's a very long way to the nearest hardware store, and thirdly because we have to maintain radio quietness at all times. So the two sites I've shown you is just the core of the array, just about half the dishes. So we're talking about 3,000 dishes and about 250,000 of those metal spiders. In both cases, half of that number will be built in this core, so here in South Africa and here in Australia, but the rest of them will be spread over the entire continent. Here in Australia, about 3,000 kilometres across in every Australian state, and in 8 other African countries. Linking all this together, and you get a dish that is this big or this big, that makes it incredibly powerful. So just to show you how radio quiet these sites are, how special these sites are, how unique these sites are, how hard it was to find one of the few accessible places on Earth that does not have radio transmission. Suppose that you wanted to build a big radio telescope in Toronto. Really, really bad idea. If you take a spectrum of what Toronto's spectrum looks like, so this is in hertz, so this is 100 megahertz, 1 gigahertz, so this is sort of the FM radio band right here. Anywhere you try and tune your radio telescope in this huge range of frequencies, just completely bombarded with junk. All of these spikes are all sorts of different transmissions from military, from police communications, mobile phones, television, and of course the biggest spike of all, FM radio. If it turns out you can actually calculate what frequency you expect to detect this faint hiss from the first stars. Remember, the whole point is to detect this glow or hiss from the first stars being born, and when you do the calculation, it comes out that the best place to look for them is about 100 megahertz, right in the middle of the FM band. So whoever picked the FM band back in the 1920s or 1930s obviously knew nothing about astrophysics, because they would not have put it right at 100 megahertz. So Toronto, bad move. You would not want to put a radio telescope in Toronto. Well, what if you put it near some small town? So there is a radio telescope in Australia in a town called Narrabri, population 6,000. I'm sure there are lots of towns like it all throughout Canada, and things are a lot better. You can see that there are a few little gaps, so if you tune your radio telescope in right there, everything's fine, right there, and right there, but there's still a lot of places where things are hopeless. I have students who use this telescope all the time, and I say, how did things go? And they say, I got nothing, because there was some military radar on or something. And in particular, at 100 megahertz, again, not as bad as Toronto, but pretty hopeless. But the Australian part of the square kilometre array is being built near a cattle station called Bellardi. Bellardi has a population of 4. And here's what things look like in Bellardi. So it's not completely pristine. There isn't a place on Earth that's completely pristine. And the reason why you still see a few spikes here is because of satellites. There are satellites like GPS and Iridium and a million other things and all sorts of military satellites, and we're not really sure what they do. But all of those are moving overhead and they're transmitting, and there's nowhere on Earth that you can get away from them. So there are little spikes from satellites, but if you zoom in, these are very, very narrow, and there's actually lots of gaps here. And they're not that bright, and they're only on some of the time when the satellites are passing ahead. So even though this doesn't look perfect, it is actually remarkably clean. And indeed, there's lots of spaces around here and everywhere else where finally you can get rid of all of that clatter and shouting and grinding and crunching of the radio sky and actually look for these faint radio whispers from the first stars being born. So this is why we're putting these telescopes in the middle of nowhere in Australia and in South Africa. Despite the great cost and effort of putting them in these very remote locations, we have to, because it's the only way we have a hope of actually seeing the signal that we're looking for. Now, building the square kilometre array is a massive undertaking. We're trying to build a telescope that's 100 times more complex than anything we've built before. So even if you wrote me a check for $1 billion right now, we'd say, well, hang on, we're not quite ready yet. So what we've been doing, well, we're getting very close to being ready. But what we've been doing over the last 10 years is building a bunch of prototypes to test the different technologies for the square kilometre array. And so here are some of them. And Canada has played a big role in much of this. There's one being built at the South African site called Meerkat. There are 2 being built at the Australian site, one called ASCAP, which tests the traditional dishes, and one called the MWA, and this is actually a drone photo of it with these metallic spiders. And there's also some prototype work being done here in Canada, here in Penticton, with a radio telescope called CHIME, which is also testing a lot of the technology. So in particular, the big role that Canada is playing, and arguably the most important role of all, is that we are designing and building the supercomputer that's going to link all the dishes of the square kilometre array together. When you have 3,000 dishes all operating in concert with all the signals streaming from each one, the total data rate that you generate is about 70 terabytes per second. So that's 70,000 petabytes per second, or 70 million gigabytes per second. It's about the same as the entire traffic of the internet every second, but just for one telescope. So this is not something you can use a laptop or even a fancy supercomputer to combine all those signals. You are taking in 70 terabytes a second from 3,000 dishes all spread throughout a continent, combining all the signals, converting it into an image, and you have to do that before the next second of data comes in. And so it's Canadian astronomers working in the universities and at the National Research Council who are building the supercomputer, what we call a correlator, essentially the brain that is going to make this telescope actually see. And so that's arguably the most important part. You can build as many dishes as you want, but without the supercomputer, you see nothing. And we are the ones putting that together. In fact, you might think this is a beautiful image. This is actually 80 meters across. It's quite large, but the most exciting thing in this picture is actually this little shed here, because that's where the prototype correlator, the prototype supercomputer is, that's multiplying all the signals together. So, of course, I don't think it's fair to ask you taxpayers for $1 billion just to answer one question, the origin of the first stars. So while that was one of the powerful, original, motivating questions for the square kilometre array, The science case for the square kilometre array has now become incredibly rich, and there's a book on my bookshelf across campus that's over 1,000 pages describing all of the exciting things that we're going to be able to do in a few more years with a telescope. But just to mention two of them, understanding where the first stars come from is not enough. Let's understand where life comes from as well. We know that stars are born in these very dark, dense clouds of gunk and dirt. So this is not a place where all the stars in the sky have died. This is actually a dark cloud sitting in front of all of these background stars, floating in front of them. This is a dark cloud where stars and planets, maybe like ours, are actually being born. And we know that this gunk isn't just things like hydrogen and carbon, but it's full of very complicated molecules. And one of the questions we have here on Earth is we do not know how life began. We know that we are descended from more primitive species, and they're descended from more primitive species. And in fact, that every life form on Earth is our 5,000th cousin going back to the very first cell. But we do not know how that cell began, and even that first cell had all sorts of complicated molecules in it, like DNA. We don't know where that stuff came from. What we do know is that some of these complicated organic molecules are actually out there in space. They're very faint, they're very hard to see, they give off very faint glows of radio waves. What we think is that maybe the building blocks of life, the molecules of DNA, are actually out there in space. And that maybe the reason why life began on Earth is because these molecules are everywhere in the cosmos, and that when the Earth formed, it was already seeded with all the building blocks of life. But we won't be able to answer that until we can detect the glow from these molecules with the power of the square kilometre array. We'd also like to know how the Earth formed. Now, we know of many thousands of planets around other stars, and we see these giant glowing disks where those stars are forming planets. But what we never actually see is the process of planets like the Earth forming, but with the very sharp vision of the square kilometre array, we will get pictures like this, where you can see the disk beginning to break up and to actually form planets like the Earth. Something very different that we'll be able to do with the square kilometre array is to understand the question of what gravity actually is and how it works. I mentioned before to you the idea of pulsars, these naturally occurring spinning clocks. And the animation I showed you before was just the one pulsar. But there's something like 50,000 pulsars in the Milky Way. The whole galaxy is just humming with the ticks of these naturally occurring clocks. So this is a physicist's dream. If any of you studied physics at high school, there's this very contrived arguments where, like, imagine there is someone in a spaceship with a perfect clock, and someone at home with a perfect clock, and someone watching them with a perfect clock. Well, this is not contrived at all. The galaxy is filled with these perfect clocks. And if you could somehow measure the ticks of every one of these clocks at once, you could actually understand what gravity is. Because Einstein's theory of relativity predicts that gravity washes across the Milky Way like someone taking a giant carpet and taking one edge and shaking a ripple across it. And so very slowly over hundreds of thousands of years, as gravity moves across the Milky Way, there should be this giant ripple that drifts across the galaxy. And you should be able to see this ripple by very accurately timing these spinning pulsars all over the sky. As the galaxy ripples, some pulsars will come very slowly towards us and others will be dragged away from us. And you would see that in the ticking of their clocks. So one amazing way to test whether Einstein was right about what gravity actually is and how it works is to use these naturally occurring clocks to look for ripples in space-time. The catch is that you need to look at tens of thousands of these pulsars all at once, and you need to do so with incredible precision. Again, the only telescope that will be able to do that is the square kilometre array. And when we do that, we'll finally know whether Einstein was right or was he wrong. I want to finish with two sort of more philosophical remarks. One is that being an astronomer is the only thing that I ever wanted to do. Ever since I was 3 years old, I wanted to be an astronomer. Other kids wanted to drive fire engines or be police officers or fighter pilots. I wanted to be an astronomer, and I never wavered from that goal. How did it start? Well, when I was very young, my parents bought me this book, which I still have on my bookshelf right now here in Toronto, this album of astronomy. And my parents bought me lots of books. I was a very hard-to-please child that needed information and facts. And there was no internet in those days, so we had to resort to books. And so they bought me books about race cars and dinosaurs and volcanoes and astronomy. And I read them all, but the one that I kept reading over and over again was this one. And the reason why is because the other books told us everything that we knew. And this book told me all the things that we didn't know. Growing up as a kid, your parents are the ultimate authority. You think that your parents know everything. Then you realize, of course, that they know nothing. I'm finding that out now from my own son. But you think your parents know everything, and then you realize there are some things mum and dad don't know, but your teacher knows. And in my day, if your teacher didn't know, you'd go to the library and look it up in the encyclopedias. These days, of course, you go to the internet. But there was this view as a child that you probably also had too, that ultimately, if you ask the right person or do the right search on Google, someone will know the answer to it. And when I read this book, I had this stunning, horrifying, but exciting realization that there were some questions that nobody knew the answer to, that I could ask as many people as I want, and no one actually knew. And the other thing that this book conveyed to me, unlike the books on dinosaurs and race cars, which just told me the facts, is this book said that we are in the process of figuring these things out, and that smart people can actually change the situation from something that nobody knows to something that everybody knows. And when I realized that that actually happened, that there are things that we don't know now that we'll know in the future because of the calculations that people have made, I thought that is what I want to do. And amazingly, when I go back and read this book now, 30 or 40 years after it was published, almost all the great mysteries in this book are now solved. But all of the great mysteries of now, like where do stars come from and what is dark energy, well, the book doesn't even ask those questions because no one even knew those were things we didn't know back then. So the thing that continues to excite me about astronomy is the chance to actually figure things out that nobody knows. And when I get to use the square kilometre array and I measurement, well, there's a responsibility on me, once I make a discovery, to publish it in the scientific journals, to tell people about it through talks in the media, and within a few years, hopefully, my discoveries become part of every textbook. But there will be that 5 minutes that no one's going to be able to take away from me, where I just sit there at my desk, and I am the only person who knows. And that is the best feeling in the universe. So just to prove to you that I always wanted to be an astronomer, and when I was about 5, my parents took me to the equivalent of the national exhibition in Australia. We call it the Easter show there. And there was someone sitting with a chair who would draw a caricature of you for $5. And I said, oh, Mum, Dad, please, 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 can I have my caricature drawn? And they said, okay, and they put out the $5. And the artist said, well, I'll draw you being what you want to be when you grow up, expecting the usual answer. And I said, an astronomer. So here is the picture of me. I'm sure you agree I look exactly the same as I did in 1978. I'm not quite sure what constellation that is, and I've switched to radio telescopes, but otherwise I'm very much living the dream. I want to finish by emphasizing probably something that's even more exciting about the square kilometre array. We don't just build a billion-dollar telescope because it's cool. We build it with a very well-defined, very precisely calculated case. We have a science case, we have an engineering case, we have a tourism case, we have a business case, we have a governance case. We're very cognizant of the fact that this telescope is going to come from your hard-earned tax dollars, and we want to make sure that we do good things with it. So we have very specific goals in mind. When we turn the square kilometre array on, we will know exactly what we want to do. And I've described just a few of those experiments to you, and one of the most important ones we want to do is we want to look to see where the first stars come from. But if you look back at the telescopes that have been built previously, things like the Hubble Space Telescope and others, they did what they were built to do. They had a detailed science case and a business case, and they indeed quite quickly ticked off the things that they were designed for. But the most exciting thing when you turn on a brand new set of eyes is that you will find things that you did not expect. And astronomy for hundreds of years has been driven by this concept of serendipity, that you find things that you couldn't possibly have realized. And astronomers have realized this for hundreds of years. So there's a lot of literature on this. There was a very famous Danish astronomer named Hamlet, and he had a PhD student named Horatio, and he was trying to explain to Horatio about his next observing run, to be aware of serendipity. And so what he said to Horatio was that there are more things in heaven and earth, Horatio, than are dreamt of in your philosophy. That there are things that are up there that, Horatio, that even though you've read all the textbooks, you couldn't possibly imagine. If we move forward to the 21st century, there's another great astrophysicist, Professor Rumsfeld, who said it in much clearer language. You've all seen this quote before. the idea of the known knowns, the known unknowns, and the unknown unknowns. So what Professor Rumsfeld was trying to say is that there are known knowns. We know of lots of galaxies, and what he meant was that there are more distant galaxies, probably not that different from the ones we have now, but we'll be able to see more distant ones with our new telescope. There are, of course, the known unknowns, things that we know must be there, but we don't know how they work, things like the first stars. But the thing that most excited Professor Rumsfeld was the unknown unknowns, the things that we don't know that we don't know. So I wish I could finish by telling you what those unknowns unknowns are, but of course I don't know what they are. But allow me to speculate. Why do we build radio telescopes in the middle of nowhere? It's so we can get away from all the radio transmissions of everyday life. But what if there is other life out there? And what if, like us, they require the transmissions of everyday life to power their civilization? So while if we put our telescope in the middle of nowhere, we might get away from the noise of our own radio transmissions, with the square kilometre array, we will, for the first time, have the capability and the sensitivity to pick up what we call leakage radiation. That if there are other worlds out there, hundreds or thousands of light years away, with their own equivalent of mobile phones and FM radios and microwave ovens, then with the square kilometre array, we might have the sensitivity to actually pick that stuff up. And so beyond all the known knowns of the first stars and testing gravity and the origins of life, maybe with the square kilometre array, we'll make the biggest discovery of all and discover that we are not alone. Thank you very much.